On this short film, I will show how to define tendons and take them into account during calculations. Let's start from background file import. I choose units and layers of DXF file, and we can start to modelize simple structure. We need to define plate contour by clicking its corner points. Here it is rectangle, but it can be any contour. During contour definition, we can choose different snap modes for points and also go back to any previous points. After choosing thickness, our plate is ready. In the next step, I will define supporting walls. There are a few possibilities, but in this case I use standard settings. So, for each wall I click two edges lines and I validate it by clicking on one of already chosen lines. So finally, we have a plate supported by 4 walls. Our simple structure is ready. It can be presented both as a geometrical model with element dimensions or as a calculation model, where only axes are presented. So now we are ready for tendon definition. Generally, tendons can be defined in 2 ways. The first method is choosing all high and low points manually and then modifying z-coordinate of each point in grid. The second one, which will be presented here, is choosing only edge points. In this mode, program can automatically find tendon supports and create high and low points automatically. Eccentricities by default are taken as half of plate thickness minus cover. When these edge points are defined outside plate, program can automatically cut such a tendon to plate contour. It is recommended when contour edges are sloped. Tendons are located inside plates, so in normal situation they are not visible. To make it possible, it is necessary to change one of material properties, namely transparency. So, if I will do it for plate material, then both plate and tendons are visible on geometrical view. Loads from each tendon are automatically calculated after each modification based on exact curvature in each point. To visualize tendon loads, it is sufficient to switch loads on 3D view and choose compression load case in inspector window. IgentForm enables easy definition of load combinations. Here I define the combination which consists of structure self-weight and tendon with default coefficients. Now we can perform load takedown calculations. After it, we can see results for all load cases and combinations. When tendon is supported by more than 2 walls or beams, then program automatically calculates supports reactions as for multi-span beam. Each tendon can be optimized manually by modifying high, low and inflection points coordinates, eccentricities and straight segments length, or exported into IgentBeam, where we can see diagrams for self-weight, tendon loads and combination. In IgentBeam also tendon root and loads from tendon are visualized. The user has an influence on tendon loads accuracy by changing segment length. It influences number of points where curvature is calculated. When we see that tendon force is inappropriate, we can simply go back, change force value and call IgentBeam again. So now we are back in IgentBeam with modified tendon force and we can start optimization. I change segment length for 0.5 meter and I open dialog with optimization options. It is not recommended to make full optimization in one step, as number of variants to analyze would be too big. So first I would like to adjust x coordinates of low points, which by default are in the middle of span, to extreme values of bending moments for self-weight. We can see on moments diagrams, then these coordinates are now well adjusted. Width of our plate is 10 meters. Let's assume that we plan to define 5 tendons. So, if we would like to equilibrate plate self-weight, each tendon must equilibrate a plate bent 2 meters wide. By using appropriate suffix, I can change this value for all spans at one time. Next step is optimization of inflection points. I choose all points. For each point we have minimum value, maximum value and step, what finally gives us number of variants to analyze. Program calculates each variant and choose the best solution as far as minimum bending moment for combination is concerned. Now the last step, namely eccentricities optimization. I choose all points except edge points, and as previously I set step. In this case number of variants is quite big, but thanks to parallel processing, calculation time is acceptable. Finally we can see diagram of bending moments for combinations. Maximum value is less than 13, so dramatically reduced. Now when I save this example, IgentBeam will be closed automatically. Now in IgentForm I import optimized tendon and it is automatically updated. As previously, we can run load takedown calculations and we see that reactions on supports from tendon loads are significantly different from loads from original tendon. Each tendon can be different and optimized individually, but in this case I simply choose defined tendon and I copy it 4 times. As icon for calculation is switched on, then calculations are performed automatically. Reactions on walls are presented in the middle of wall. Now example can be saved and restored at any time later. Now we are ready to connect with Autodesk Robot Structural Analysis program. So I choose Export to Rtd File. When any version of robot is installed on computer, IgentForm will use a Robot API to save the whole structure and tendon loads into Rtd file. This possibility is a great added value for robot users and enables them to design prestressed plates. I open Autodesk Robot Structural Analysis program with currently saved file. I choose Loads Layout and I display Compression Load Case. We can see big number of load records, what is practically impossible to do if we would like to achieve the same effect directly in a robot. For verification, we can switch back to IgentForm to see load cases. It seems that transfer is correct. Now let's verify results in robot. I run calculations with default settings. IgentForm models are of very good quality, so usually there are no problems during calculations. I choose Results Layout, where I switch displacements on Z direction and also set appropriate projection, namely top view. Now I go to Preferences to increase accuracy. I choose millimeters for displacements. We can see that displacement for self-weight is about 3.5 mm. After switching for compression load case, we see nearly the same displacement, but in opposite direction. So finally, for combination, we have less than 0.1 mm. It means the tendons balanced plate self-weight. Finally, I go back to IgentForm to look at load takedown results. We see that tendons significantly reduced support reactions, so they must be taken in analysis. Thank you very much for your attention.